So we're going to start now. So this paper is large language diffusion models. Hopefully everyone here is a little familiar with diffusion models. You know, it's like generating left to right and it's autoregressive, right? So we'll talk about, first of all, autoregressive models. So why are we looking for alternatives, right? Like ChatGPT and like all those models work really well, right? Like they can generate amazing text, they can write poems. Some of you probably use it for homework, right? So why are we looking for alternatives? There's a number of reasons, but first of all, a lot of like scientists like Jan LeCun and like other people don't like autoregressive models for a number of reasons. Jan LeCun is probably one of the more opinionated people. He says autoregressive models are doomed in big red text, so that's pretty shocking. The other reason is because autoregressive models have some pretty interesting issues. Like for instance, they can't go back and like correct their output. So like for instance, in Anthropics, like on the biology of a large language model, they basically like looked at like jailbreaks, and part of the thing that makes jailbreaks work is the model will basically like start generating text, and then it doesn't actually realize it's a jailbreak until it's too late. But then like it is basically pressured into conforming to grammar, and then it like basically completes the sequence. So there's a number of issues with autoregressive models. You can read Jan LeCun's opinion. It's kind of an opinion, honestly. But basically, his take is that kind of like autoregressive models have like kind of like compounding error. So like it generates one token, it's not like optimal, and then it gets worse and worse over time. And so basically, the reason we're looking at diffusion is because if you look at other domains like image synthesis, obviously like stable diffusion, flux, all of like the big image synthesis networks are all like diffusion based. If you look at like audio domain, there's Tortoise TTS, and then the other thing is diffusion isn't always like convolutional neural networks. There's diffusion transformers and things like that for image generation. So we already know that diffusion is a strong alternative to autoregressive modeling. Autoregressive modeling is not used in like image generation really, or like speech synthesis. So that's why we're trying to bring it here. So LLaDA is the alternative to kind of like autoregressive modeling. It's basically an attempt to use this thing called masked diffusion modeling, which we'll get into in a second here. So first of all, why do we care about LLaDA? Because it's basically like one of the first models to scale to like 7 billion parameters, and they compare it against some other large models like DeepSeek, Qwen, and Llama. So they have like a comparison chart here. So for its size, LLaDA has basically like state-of-the-art accuracy, which is impressive because, for instance, Llama has reinforcement learning and like stuff like that. But LLaDA is actually only trained in 2 stages. It's trained in it only has like pre-training and then supervised fine-tuning, while Llama has like that, and then also like reinforcement learning on top of that. So as you can see, it's kind of like well-rounded on like a few benchmarks. The human eval, CMMLU, C eval, blah blah blah. The metrics that they chose might have been like a little cherry picked, to be honest, but we'll get into that a little bit more in a second. So here's like kind of like the big chart, which we'll get into later. It's kind of interesting. They trained an autoregressive baseline, which is interesting too, because when we get into the architecture, you'll see that like there's basically like no changes between like an autoregressive model and LLaDA. It's almost exactly the same thing architecturally speaking, but they claimed like some pretty big performance increases in quite a few things. So we'll get into that. So what is it? So LLaDA is a masked diffusion language model. Most of the architecture is familiar. There are a few key differences, but honestly, they're really small things. So what is a masked diffusion language model? Masked diffusion language models basically predict the whole sequence at once, and then have like a thing where they only keep high confidence tokens. So if you look here, you can see that it keeps the and then the end of sequence token, but it gets rid of these two, and then it just like remasks them. And then over time, it'll like slowly kind of come to like its answer, where it'll eventually be the answer is 4. So it'll basically like go through and like remask tokens or keep tokens depending on like its confidence. The advantage of this is you can actually stop it at any time. So you could stop it here, and then you'd have a sequence, but it would have been wrong. So there's a trade-off between like performance and quality. You can kind of like tune yourself to whatever you want. The other thing you'll notice too is that it can actually go back and like edit its previous outputs. So you see here, it keeps the end of sequence token, and also the result is, and then here it keeps 4, but it gets rid of is. It can go back and like change words around if it wants to. And the other reason is because they can kind of do that, it doesn't have like compounding error like autoregressive model. So actually, if you look at
Just one question to go back. I don't know if they mentioned this, but how do they differentiate between in your sequence of tokens the prompt token and the context tokens?
They're actually separate. So if you look at like the paper, they're actually separated like literally just like as a template. So we'll get into that in the supervised. I'll talk about it in a second. Okay. Yeah.
After masking, can it unmask a token?
What do you mean, like after masking?
After unmasking, can it mask a token?
Yeah, we'll get into that too. There's a few different strategies they use. So actually, this paper is a little convoluted, and some of the stuff is actually answered on their GitHub. So I'll get into most questions at the end. Okay. So LLaDA is actually basically just transformers. This is from their GitHub in guidelines to MD. It's basically like some of the code that they had. So basically, there's actually no specialized mechanisms. Like they didn't like make special positional embeddings or like system level architectural optimizations for LLaDA. They use SwinGLU. They have rotary embeddings. They have RMS norm, and they have just like a transformer encoder for the mass predictor. And that's pretty much it. The differences are they have non-causal scaled dot product attention. They don't use KV caching. And the attention layer has more parameters, relatively speaking, and they reduce the feed-forward network dimension. And the reason they did that is because they wanted to maintain comparable size to like Llama and like Quant and stuff like that. So LLaDA is actually trained in 2 stages. You have unsupervised pre-training, which is just like large text corpus, and you have supervised fine-tuning. The unsupervised pre-training is basically where it like attempts to like learn like kind of like the underlying distribution of language. They train on 2.3 trillion tokens on 0.13 million H100 GPU hours, and then they have supervised fine-tuning on 4.5 million instruction pairs. And it uses cross entropy loss. Their learning rate schedule is basically just like it warms up and then it's constant. And yeah.
Sorry, the pre-training has to be supervised, doesn't it?
No, it's just like it's just like dumped on text, and this is what they said in their paper. It's
Yeah, but like you make a text prediction every time, or how do they do it? Because like regular training is like even for regular LLMs, the main training is still supervised. Like you do next token prediction and you check with your corpus.
right. So I think by unsupervised versus supervised, they mean like kind of like you like kind of like I guess like filtering, because like what they said in the paper basically is they just like dumped text on it and then like had it work. So they basically like used I don't remember what the dataset they used was, but they kind of but they basically said what it was in here.
Because like unsupervised and supervised are like 2 very specific terms. Like it's in
Yeah.
it might just be
sorry.
like the paper misuse.
It might be, but it is basically what they said in like guidelines. So I'm not too sure, honestly. They basically the way they kind of like said it is that it's just like I think what they meant is that like it's labeled versus unlabeled, if that makes sense. Like so basically what I kind of got from it is that the first stage is like they just like kind of like give it like text and it was like text completion, and the second stage it's actually trained differently. So it's like it's like a prompt and then like instruction result. So
Okay,
I think that's what they meant.
Yeah, okay. So yeah, I think this is just forwarding on my part, because like the first stage is also supervised training. But
Yeah, if you also like read some of the stuff they said, like there is a little bit of like linguistic issue, I think, because they're Chinese author. So like also like in the paper, some of the like stuff was like in Chinese, and I can't read Chinese, so.
yeah, that might be an error just in translation.
Maybe, but also like I'm not sure. I'm pretty sure what they meant is that unsupervised pre-training was like just like they just like trained it on like large corpus, and then the supervised fine-tuning was just for instruction following. I'm pretty sure that's all they meant. Hello there. So anyway, the supervised fine-tuning phase is basically just like where they're like training it to like do instruction following. In their GitHub, or sorry, in their GitHub they mention like complications from it, but like it's a little weird. They basically say during supervised fine-tuning, each sequence is a complete sentence, whereas in pre-training, many sequences are truncated. As a result, during sampling, given a generated length, regardless of whether it is long or short, the instruct model tends to generate a complete sentence, unlike the base model. It does not encounter cases where a sentence is only partially generated and needs to be continued. So there's a little bit of issue there. I'm not actually sure what dataset they used, didn't specify, which is kind of interesting. But anyway, so actually in the inference stage, we were talking about this earlier. I think the question was like, how do they like, remask tokens. So there's kind of 3 different ways inference can work. You have random remasking, which is basically just like at each step and during the reverse process, like the model just like predicts all current tokens, and then to proceed, it just like kind of just like randomly like remask stuff. And then the second way is like low confidence remasking. So like later on, if it like gets less confident in a token, it like remasks it. And third way inference work is like kind of like a little interesting. This is just supposed to say semi-autoregressive. Ignore the origin part. That was something they said didn't work. So basically, it generates it in chunks. So you have like you basically have like a chunk, and then you do the diffusion process on that, and then you like go on and do another chunk and do the diffusion process like that. So that's kind of the 3 ways like the diffusion process can work. And also, I forgot to mention it too, but I think the other question was like how do you differentiate like prompt and thing. So basically, what they do during like supervised fine tuning is the prompt is like not masked at all. And so you're only actually like computing the loss on like on what the response is supposed to be, and like the template they use for that is the model actually like learns like how to predict the end of sequence token. So like they have like a whole like template, I think it's in here, where it's like end of sequence or whatever, and it might be in guidelines also. But so let's see here, but like so they have like a prompt template, and like this is an example of like another Chinese thing. Okay, I think it's in guidelines actually.
I mean, it's also, are you saying like they trained it to not predict everything for a specific token?
No, it doesn't predict the. So basically, they separate the prompt and the like actual what the response is supposed to be. They give an example. I don't remember where it is. They give an example of what their like actual like formatting is though.
Because regular LLMs, like they do next token prediction, but like the context side, like the context window is always the same, right?
Mm-hmm.
So for something like what they're doing, you still need to have the same context window. It's going to be like all your prompt tokens and the current response tokens.
Right. I don't actually know where they're. Oh yeah, it's right here. So this is what it looks like.
And it's very hard to do.
Yeah. So this is like what their like supervised fine tuning phase looks like, and it's kind of like what the thing would look like. And so they only mask like part of it. They only mask like the model, the model's supposed to predict, and then everything else. They replace it with mask tokens. So as an example here, like say that this is like what it's being trained on, right?
Mm-hmm.
So you have like the assistant phase here. You replace this part with mask tokens, and then it's like supposed to predict it. So the way that they do this is they choose like a random like basically random value between 0 and 1, and then that's like the mask ratio, and then the tokens are like each individually masked based on that as like a probability. So like this can be entirely masked or it can be like basically not masked at all, and then it's just like basically trained on that.
Okay, yeah. So they essentially train everything before to not be masked, or like for the model not to try to mask everything. Okay. Am I right?
So actually, okay, so there might be a little confusion here. So during like the actual inference process, basically what would happen is this part would be like completely unmasked, right? There'd be no mask tokens here at all. But then it would like basically just like for the first step, you basically just give it like a fuck ton of like, you give it like a lot of like mask tokens here, and then like learn to predict them, right? And the other thing is too is so this is like an example of what inference would look like. It can basically like spam end of sequence tokens to like end the sequence, right? So like the purpose of this is like so it can like generate. You can like choose how long it wants to generate for. So does that kind of make sense?
I mean, this is like every other LLM. Like, my question is how did it, because you said like it can make a token into a mask token, right?
Yeah, and that was the remasking that we talked about here.
Yeah, I guess the answer to my question is like they train the model to never remask anything in the prompts.
No, so the way it works is it's based off of the confidence in the token. So like if it's confident that the token is like where it's supposed to be, then it's kept. But if it's not confident, then it gets rid of it and it remasks it. So if you look at like their GitHub, you can see like the actual like inference code.
It has to choose which area could be remasked, like which tokens in your sequence could be remasked, right? Then there's a set number of those tokens that are from your context. Like I'm gonna call like the limit between the two, like the X token, which it tells you everything before X token was your prompt and your context, and everything after the X token is your current answer. So everything before the X token, like those, you're not allowed to change.
Right.
They're already set and stuff.
Right.
Like your what is 2 plus 2 or your previous conversation.
Okay.
So my question is like, how do they prevent that?
I think I know how to do that. Like usually what they do is that the transformer mask that they have, the Gaussian masking, that itself sets, whatever the output is from that, it is masked off.
Oh.
Not by the mask token.
So they use non-causal attention because so basically I think I get what you're saying. Are you asking what makes it like not predict this?
Yeah, how do they prevent new predictions on the existing prompt, knowing that the existing prompt didn't have any size?
So basically in their inference code, they basically just like ignore anything between like the two tokens. So it just gets ignored. So even if it does predict it, it doesn't matter. But also like in the actual like training process, they have special tokens which are the mask tokens, and then also like these types of things too. So so basically like so it's like this type of thing, right? So it's start ID, user ID, blah blah blah. So it basically knows what's like given by the user and what's not.
Okay, so the answer is they're ignoring it. That's what I was looking for.
Yeah.
Okay, I wasn't sure if like there was some special structure they used to separate your input and output.
No, it's just like they just use special tokens for that.
Yeah, that's like every other LLM. Okay.
Yeah, it's just like every other language model. Okay. Yeah, and then so inference can work in 3 ways, and then summary of architecture. Basically, mask tokens independently, mask ratio 0 to 1, and then it predicts them. You take cross entropy lost during stage 1, and then it just is trained like that way. And then for stage 2, prompts, this doesn't get masked. This gets masked, and you only calculate cross entropy on like the tokens that it predicts. Or sorry, only mask tokens. And then, so during the inference process, you have the prompt, you have a response, and then you only like infer on this, and you just ignore anything it predicts on that. So any questions? It's pretty simple, honestly. Yeah.
How does the model learn how to remask? Because I think you mentioned earlier that it's random masking. So is that manually done while training, or like can the model learn what to remask?
Okay, so to summarize, there's two processes. They're both based off of confidence, right? So basically what happens is if the model's confident in something, you add it, right? But let's say like this is where we're at, right? Let's say that this is like 2 plus 3, right? So the answer should be 5. It has already output this, right? The way it would work is that it would predict the sequence again, and then it would like think that this is like low confidence, and then it would get replaced by a mask token. So the model doesn't like explicitly like say that I think that this should be remasked. It just says I'm not confident in this, and then like the actual inference process will remask it. Does that make sense? There's low confidence remasking. Yeah.
Just a small question on this. So is the output of the model at every step?
It's the whole sequence.
Context window, time, like context window times the size of your token, like the number of tokens you could have.
Like you're talking about like the output dimension?
Yeah.
I think so. So let me like actually check. So they have.
Like a regular LLM only has like one row for the next token.
Right.
Or one column, sorry, but one column vector output, where it's they just run softmax on it. And usually will pick the best, or they'll have like some randomness.
I think the output is actually fixed size on this one.
The output should be like because from what I understand, like you're predicting the whole.
Right, you're predicting the whole sequence at once.
Okay.
Right.
So that's probably a limitation of the paper, right? Because predicting the whole sequence is very expensive.
It is very expensive, but it's expensive, but you can like during training you change the sequence length, so it's like kind of like language model like that where you can have different sequence length. I think they train it on actually not that large of a sequence length, but I don't really remember what it was. To be honest.
Yeah, I mean this doesn't seem like it can go to like 1 million.
No. It's not like that. It's kind of like exploratory paper. It's a few months old as well too. So there's actually another paper too called LLaDA, which is trying to like go like to higher sequence length, but I don't actually, to be honest, remember. I haven't read that paper yet.
That's not, okay. That makes sense. I was just double checking it, so the output dimension.
Yeah. I think they might mention the context length. Context
I know
length.
that's like one of the major reasons why regular LLMs work the way they do in an ARM fashion is because like you don't have to re-predict the entire thing. You just predict one token.
Right. But the third advantage is that LLaDA can actually predict more token at once. So like, as an example here, it predicts like 2 tokens at once, and it keeps them. So so the other advantage is like like I said, it can predict like more tokens at once. Like I think like an actual inference like averages like 4 tokens per pass. So like even if each like samples are more expensive, then it like takes less of them overall. So it's like it has like some advantages there, right? So it actually ends up being, I think, cheaper overall. But that was like what was said in another paper. In here they don't actually like specify that. That was in Mercury. So are there any other questions on this type of thing? Yeah.
Sorry, go ahead.
How exactly does like the model like predict the confidence? Because you said like it then goes back and says which one it's not confidence in. So is that just like
What is this? Just like what?
just entropy, right?
So it has So basically, you know like how like normal language model works, right? Where it's like distribution. It's basically like the same. I think it's basically like the like kind of like same thing here. So if you look at the, what? Sorry.
Nothing. Thank you.
No, okay. Well, okay. So just as a recap, it's like it's literally a transformer, but like there's like 3 changes, and like the inference process is different. That's like basically it. But so basically like the way it predicts confidence is basically just like that, and then it's like, and then like if like the like likelihood is like high enough, then it gets added, right? So yeah. And then you had a question too? Oh, okay. Any other questions?
You run softmax on like all the tokens you could be at any point. And so softmax returns like makes everything probability between 0 and 1. So you probably put like a cutoff node like 0.1, something like that, or 0.2.
Right.
And
And
above that you just set it instead.
right, and it also is a little iffy too, because you can change it from so actually they mentioned this earlier. So semi-autoregressive origin, they actually mentioned didn't work well, but they never like really specified what it was. So it's actually not in the paper. It's in their GitHub. But so origin. So yeah, it's worth noting similar argument origin was not mentioned in our paper in order to divide corresponding code. However, we include it here because we believe that sharing failures is blah blah blah. Blah. And then so yeah, you can like look at like the code here if you want to as well. I can zoom in if you want on anything that's interesting. Any other questions? Are we good? Yeah.
I'm gonna be annoying.
Uh-huh.
Do you know if they have any sort of hidden states between each iteration? I know that's been like one of the ways that some diffusion has improved is between each iteration, just to have like some idea of what's been going on. You keep a hidden state for your model to keep track of things.
They don't.
They don't?
No. It's just no. That's something that would be even more like. So actually, mass diffusion is only one way to like have diffusion language model. There's also like discrete. There's also like discrete diffusion, continuous diffusion. I think it'd be more like a continuous diffusion language model. But this is a mass diffusion language model, so it's just like tokens and that type of thing. They don't actually like. They don't actually keep track of anything. That's also why they don't have key value cache or causal, or and they have non-causal dot product attention. So.
Yeah, I understand why the other ones don't really make sense, but like that might be just a room for improvement. Like if they try to do this.
Yeah. So actually, this paper is a few months old, and so it's like I said, it's not that like complicated or like a big deal. The reason I wanted to bring up this paper though is because it's like kind of like the foundational thing, if that makes sense. There's a lot of papers that build off of it that I also want to go over as well. So I think someone mentioned like context length as well, right? Like the kind of small context length. There's other paper too that's called LLaDA as well that has more context. Hold on, let me like pull this up real quick here. There's also like LLaDA and things like that too. So there's more interesting things like that. So diffusion language model. So there's like a guideline here as well on like GitHub, which is like basically like a collection of papers. And so what we would probably want to go over is like things like this. So like you can like see kind of like all the way back towards where it was earlier. So we have LLaDA 1.5 and like things like that all the way back here. So it's a 2025 paper, but it's kind of old. So you can also see like the key here. There's discrete, continuous, like multimodal. So you can kind of like look at what has been done recently. So LLaDA's over here in all the way over here. I think in like February or something. And there's Gemini diffusion and things like that. But LLaDA was like, it was basically like the first like large open source language model, if that makes sense, for like diffusion. And then there's like things that came after like Gemini diffusion and then Mercury. And then you can also see here like LLaDA vision, LLaDA, blah blah blah. So there's a lot of descendants of LLaDA. So the reason I wanted to go over this paper is because I think in the future we should probably cover things like long LLaDA or like this type of thing. So it's a very simple paper, not too much in depth, or I guess like decently in depth, but like not groundbreaking. But I think in the future we should probably go over like things like this. So that's my intention. Any other questions or comments, concerns?